Alright, so you're tasked to determine differences in a new way of producing a specific polymer, and you're given an Excel file where the amount of energy, or excuse me, power, there's a difference. Power is instantaneous, so kilowatt hours is what we're going to end up with later to try to determine and do a conversion to BTU. But right now we're given everything in kilowatts, and kilowatts is a measurement of power, kilowatt hours is a measurement of energy. So just like BTU. So every 5 seconds we're given the data logger records the amount of power that's being used by the machine. It's in column AA in the Excel file. That's in this column here. It's actually recording 3 phases of power. There's 1, 2, 3, and then we've got the total kilowatts here. Alright, so we're given this assignment where the manager wants to know if there's if the renewable polymer that we're making is helping with energy costs compared to PVC. We're given the data for 22 minutes 25 seconds, and the production of the polymer with all the equipment is 0.3 pounds a minute. So that's what we're tasked to do. We know that PVC takes 12 million BTU per 1,000 pounds, and in the real world probably have this in kilowatt hours per pound, or kilowatt hours per 1,000 pounds, or kilowatt hours per ton usually. But this is the unit we're given, so we're going to try to figure out how this works, or how this compares to the PVC. So the first thing we need to do is find the average kilowatts that are used. So I'm going to hit equals average command in Excel, and then I'm going to hold down the control button, left click, keep my finger on the control button, hold down the shift button, hit the up arrow, let go of the control key. So I'm still holding down the shift key, and then hit down arrow. Now I'm still holding down the shift key, and we hit 0, which is closes that bracket, and that's it. There's our average. I'm going to hit Control X and then come down a couple and hit Excels and hit Control V there, so it's a little spaced out a little better. Alright, so this is our average kilowatts that we're using. We also need to know the time. So we were given the time is in our time is 22 minutes 25 seconds. So let's see, 22 plus 25 over 60. Let me put an equal sign in the front of it. There we go. It's 22.417. And then we also need to know our production rate in pounds per minute, which is 0.3. Alright, so now we can get our total mass produced in 22.417 minutes. That's equal to the production rate multiplied by the time. So we have produced 6.725 pounds in this amount of time. Alright, to change this, we want an energy per mass. That's what we want. Energy per mass. So let's convert this to energy. How do we do that? Well, we multiply by time. And we really don't want kilowatt hour minutes. That's kind of difficult to convert. I mean, you can still convert it, but let's turn it into kilowatt hours first. How do we do that? Well, first let's put our time in hours. So we just take the minutes divided by 60. Alright, and so now we're left with multiplying the average amount of kilowatts multiplied by the hours. We get 18.47 and change kilowatt hours. Not to be that exact. Meters probably not that exact. Your significant you probably only need to take it out to 1 or 2 decimal places. Probably just 1, to be honest. So 1 decimal place would be good there. Alright, so at this point we've got energy and here, and we got mass here. So we can take this energy, divide it by our mass, and this is in, what's our unit? Kilowatt hours per pound. Let's turn that into BTU per pound. So how many, let's ask our friend Google. kWh to BTU. Here we go. Control C, copy that. Control V. So I'm going to say equals 3412 times the kilowatt hours, and now I've got BTU per pound. But that's not exactly comparable yet. We still need it per 1,000 pounds. So we're going to have to multiply 1,000 over 1,000 to get it per 1,000 pounds. So take this number and multiply it by 1,000. So now our units are in BTU per 1,000 pounds. So that's a lot. That's 9,372,000 ish. So how does this energy required to produce new polymer compare? Well, 9,372,000. So that's, we'll just say 9.4 million BTU. This new polymer is less than 12 million BTU requirement for PVC. So this is both per 1,000. So it looks like the new polymer wins, this new bioplastic that you're creating. Maybe not necessarily on the capital expenditures or maybe other capital investments or equipment that you need, but as far as the operating costs, whatever you're doing is lower than the amount needed for the PVC. So this is I guess the final answer is that this one wins. That won't be necessarily the case in every situation or every traditional polymer that's made, but this is just a example of how to try to figure something like this out if you're ever given a problem like this.